Doing the lecture 3. We talked about beach marks or striations that are indicative of a fatigue type of failure. So what are some of the ways in which you can avoid fatigue when you are designing a component? You have to do post-processing of your component after the part is made. And why is that required? So the less defects and impurities you have, the less chances for the component to start failing at that point. So suppose you are making a gear, okay? After you make the component, you have to do machining, you have to do polishing, and you may even have to do some heat treatment, special types of heat treatment in order for you to improve the fatigue resistance of your component. So for example, so on the right hand side you see the SN curve. S is the stress that you are applying, N is the number of cycles. So if you just did machining or just did polishing only, you will see that you can only apply a maximum. So in this case, this is for a cast steel. So you can only apply 138 megapascals in load during the actual operation. So that, say for example, this is for aluminum 7050. T7651 is the heat treatment process. So if you do that, you will see that it has a maximum fatigue stress limit of 138 megapascals. But suppose you change the material to titanium 6 aluminum 4 vanadium type of a material. It immediately goes up to almost 250 megapascals. And if you took that component and you did short peening, what is short peening? You apply this component with uh, multiple impacts of small balls of stainless steel or lead. In the olden days it used to be lead, but I think nowadays it is stainless steel balls. So when you do that, you are applying a small amount of compressive stress on the surface. When that happens, its fatigue resistance goes up tremendously. So from 250 megapascals, by short peening alone, it goes up to almost 300 megapascals. So that is approximately 25% improvement in fatigue resistance. Okay, so different heat treatment processes and different manufacturing process can improve the fatigue resistance of your component. So for example, this one is for only for this is for cast steel. So if you had done fine polishing, it increases the ultimate tensile strength, but it does not reduce the fatigue resistance at all. But suppose your component were corroding, then it can drastically reduce the ultimate tensile strength and your fatigue resistance at all, fatigue strength at all. Okay. So if you took only as cast, hot rolled, it may, as you increase the tensile strength, it also decreases the fatigue resistance, fatigue strength of your component. So you have to do post-processing of your component after you make it in order for you to get good fatigue strength. The other thing that happens is that the composition also makes a huge difference. Say for example, if you have a carbon steel, regular carbon steel, and you are adding carbon to it, your yield strength might go up, your tensile strength might go up, but its impact energy goes down drastically. And if your impact energy goes down, what you can also assume quite easily is that its fatigue resistance also goes down. So increasing the strength is not always the ideal thing to do, especially for fatigue resistance. So here are some tables of mechanical properties um, of selected high strength steels. So here you have, um, so you can see that as rolled, hot stamped, etc. Its tensile strength goes up, your yield strength goes up, but it doesn't mean that its fatigue resistance goes up. The other thing is that its strain hardening exponent also goes up or changes. So this will tell you how easy or how difficult it is for you to make a component from that material. So I don't know if you have heard the name Michael Ashby. So Michael Ashby came up with so there are so many tables all over the place for material properties. So Michael Ashby thought that you should be able to put all this data into one single table so you can kind of figure out, what is the tensile strength that you require, what is the um, what is the total elongation that you can get from these materials, etc. And once you know that, you should be able to figure out what is its effect on other properties. So once you know these properties, it can easily be used in your design uh, determinations. Okay, so it will control the dimensions of your component based on its properties. So here are some uh, room temperature mechanical properties and some applications. So if you see that stainless steels, so if you have 304, if you have food processing equipment, brewing equipment, cryogenic vessels, etc., you can use 304. But if you want high corrosion resistance also in on top of that, you will see that you have to do 316 stainless steel and or 316L stainless steel, which is by adding magnesium, molybdenum and some additional amounts of carbon so that it forms molybdenum carbide and strengthens the grain boundaries of your stainless steel material. I may have asked you if you guys been to the Student Access Center at Stillwater. So there is a engine, GE engine um, exhibited there, and this is a similar engine made by Pratt and Whitney. So you can see that these are all, I mean, um, the components all have extremely high tolerances. So, the gap between the edge of this blade and the wall of your container would probably be less than a millimeter. So suppose something happens and this component fails. What do you think will happen to your outer container wall? It will easily puncture and throw out this component. Okay, so here are some examples of different alloys that are used in making this component. So this titanium alloy, or there could also be nickel-based superalloys, um, etc. So it depends upon the material and the property that you get. You can use different kinds of materials. Some of these are from very old. So nowadays they are using ceramic matrix composites for making these kinds of components. So here are some examples of various aluminum alloys, um, rod aluminum alloys, rod magnesium alloys, rod copper and brass alloys, rod bronzes, etc. So these are all different uh, materials and applications and things like that. So see here, this was what I was telling you, MAR M246. So that is a additional variety of the MAR M200. You can see that the application is jet engine blade. So if it is MAR M432, you will see that it is integrally cast turbine wheels, etc. So that finishes lecture 3, and we will go to lecture 4.